This is the file we worked on last time. This file contains crucial data and information that we have been analyzing and modifying over several sessions. Understanding the context and previous changes is important to ensure continuity and accuracy in our current work. Here, we will mainly focus on the serial event section at the bottom, where we will stack the data into the buffer. This section is critical as it determines how data is managed and stored efficiently. First, I will specify the necessary variables to receive the data, ensuring that all parameters are correctly defined and initialized is essential to avoid any potential errors or data loss during the process. First, we will indicate the position of the array list buffer, then specify the length-related variables for the incoming data. I will remove the serial event section and eliminate these elements, setting it to loop infinitely, while the port variable is greater than 0. This is a crucial step in ensuring that the system operates continuously without interruption. Then, regarding the byte, in the processing section of the serial library, if the return value of the read command is 1, it means failure, indicating that the data was not read successfully and that there may be an issue with the connection or the data source. In the event that the variable b, which is a crucial parameter in our system, is determined to be negative, should we consider the necessity of looping through the entire process once more and ensure that we initially reset the switch IDX buffer to its default configuration before proceeding to change it to the KS0SX setting? And then, if it is not STX, then perhaps if it is not. Clear the buffer, which is a temporary storage area used to hold data while it is being transferred from one place to another, and, if it matches the required criteria, put it in the buffer for further processing. Raise the ideas buffer, which involves elevating the priority or visibility of certain ideas within the system, and then we move on to the local area network, LAN. Since it's a LAN, which is a network that connects computers within a limited area such as a residence, school or office building, we need to organize it to ensure efficient communication and data transfer. The value in the LAN area cannot drop below 3, as this is the minimum threshold required for optimal performance, so if it's less than 3, that is considered an invalid value. In that case, we break out of the loop to prevent errors or inefficiencies. If it's valid, we put it in the buffer for further use. For KS2 and CMD, which are specific commands or protocols used within the system, although there is currently only one command, we should be able to check if multiple commands arise later, as this would allow for greater flexibility and adaptability in the system's operations. Therefore, we use the command get bm 2.8 break to ensure that the system can handle such scenarios. Understood. So you add it, and from then on, it gets stacked in the default. When it stacks in the default, you use rs buffer addb, and then you keep adding to the buffer. If rs buffer is now greater than or equal to the real length, then it means it is completely full. In this case, then, This is Now we are converting it to a native int array, right? This involves taking each element from the array list and transforming it into a format that can be directly used as an integer array in the system. We change the array list like this, initialize the IDs buffer, which temporarily holds the converted integer values, and then clear the Rx buffer to ensure no leftover data interferes with the new data processing. First of all, since this is full, the last received byte will be ETX, which stands for end of text. We check whether ETX is packet TXT or not, as this step is crucial to verify the integrity of the data packet. If it is not, we exit the process to prevent any potential errors or data corruption. If it is absolutely essential that it is determined to be correct, we will now carefully and meticulously create an instance of the specific packet we have set up earlier, insert the values we just prepared in a detailed manner, and then thoroughly call the packet check function. However, if this fails, we will break out of the process. Since it was successfully completed, we will also retrieve the data link in order to ensure that the process is completed without any issues. In the following step, it is essential for us to successfully receive and process the incoming command that has been sent to us, ensuring that all necessary protocols are followed. Next, we need to receive the data now. To execute the task in that particular manner, the command will now be dispatched using a switch statement. This approach is quite efficient and adaptable. At present, the only available option is PM 2008, which serves as a placeholder or a starting point. However, should the need arise in the future, you can easily incorporate additional options or commands into this framework. Initially, for the bolt case packet command, we retrieve PM 2008. As demonstrated, we transmit a total of 25 bytes of data, ranging sequentially from byte 0 to byte 24. This process ensures that the data is accurately and effectively communicated, maintaining the integrity and reliability of the transmission. Basically, if the data is not 25 bytes, it means we need to check whether it is 25 bytes. In the event that the value of data 0 is not equal to 0, it indicates that there is no error present. However, if it is indeed 0, then the process should be halted immediately. Moving forward, starting from the index position of 1, we will proceed to extract 2-digit values sequentially up to the 24th index. These values represent the 16-bit sensor readings that we are interested in. Each of these sensor values will be directly inserted into the CSV, which is our designated storage or processing unit. Given that the value is 12, we will perform the operation of 12 and increment the index I by 1. Subsequently, we will output the results directly to the data stream, which should sequentially display the numbers 1, 2, 3, 4, 5, and 6. This sequence implies that we will execute the operation of multiplying I by 2 and then adding 1. For instance, when I is initially 0, the result becomes 1, which is then processed accordingly. Furthermore, when dealing with the high byte data, the operation will again involve multiplying I by 2 and adding 1. This means that when I is 0, the result is 2, which is then utilized in the subsequent processing steps. This detailed explanation ensures that each step is clearly understood and accurately represented, maintaining the integrity of the original information while expanding on the details to meet the required character count. So, as you might already be aware, the indices 1 and 2 are set, right? But now, fundamentally. And essentially, we shift this and combine it into a 16-bit value, which is then printed directly. In this particular scenario, this process is done a total of 12 times, but in this case, It is important to note that there is no need for a comma at the end. Please make sure to use the output print statement only while the variable I is less than 11. In the specific case, when the variable I is exactly 11, you should output the result without including a line break. This is because a line break is not needed when I is 11. This is the correct way to handle this situation, and we are good up to this point. Following these instructions ensures that the output is formatted correctly and adheres to the specified conditions. It is important to pay attention to these details to avoid any potential errors or issues in the output. If we have come this far, please ensure that you input the edited data so that we can clearly see it in our terminal display. The remaining part of the task is that instead of automatically sending the sensor values from the Arduino board, we have configured it to send them every single time we make a request. Ideally speaking, we will make a request once every second and then try to clap. In this particular case, we do not need the buffer until then, and I will change the frame rate to exactly 1. This essentially means that the draw function will execute once every second. Additionally, I will add one more variable, which is packet text packet new packet, and here we will initialize the packet. For the text packet, we will generate the packet with package indirect pin 1008. Since we do not need data for the request, the packet is now complete. Next, when it is called, we will use mybolt write text packet and get bytes to send the bytes. However, we forgot to create the byte-related array last time, so I will skip that step for now. To create a native byte array, you first need to determine the size of the buffer. This can be done by using the new byte keyword followed by the buffer size in parentheses. Once the byte array is initialized, you can proceed to use a for loop. In this loop, you will declare an integer variable to represent the file buffer size. The loop will iterate over each byte in the array, processing them one by one. This method ensures that each byte is handled individually, allowing for precise control over the data processing. Additionally, you can when you input this integer, there is a command for it. Specifically, there is a byte value casting command, so if you do it this way, and return byte, there won't be any errors here. For example, in this particular case, therefore, in this manner, consequently, there won't be any errors. Let's do it this way, making a request every second, receiving it in the serial event and passing it. I'll run it once to see if it works well. First, I'll delete the CSV in this folder. I've deleted the CSV in the folder, and now, when I run it, I see edited appearing every second, which means it's successful. This is based on the Arduino program I wrote a while ago, which only sends data when it receives a request. Now, while it's connected, every second, the draw function is executed, sending requests, and then passing the responses successfully to show edited, just like we did before. When a specific button is pressed, it turns off, so pressing the spacebar will turn it off. Now, let's check if the CSV has been created properly. The CSV has been generated, and when I click on it, I can see that it is neatly saved like this. The CSV is not showing any erratic values like we used to see. Instead, it accurately checks the packets, so there are no incorrect values, just precise entries. Last time, I used the packet class to send requests to the Arduino, and then received and passed the response data to save it in the CSV. In the next session, I will show you how to save it in SQLite instead of CSV, which is a lightweight RDB. Then I will see you next time.